Okay, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Or, yeah, just genetic algorithm in general. By now, I don't think I'm actually covering. I've actually finished covering all the basic stuff. Well, very much into the intermediate level, I think. I don't know. I still haven't done any actual literature research, so I know that I'm aware that I could be trying to reinvent the wheel, or trying to solve a problem that is unsolvable, or trying to solve a problem that isn't actually a problem, etc., etc. So, hold on. The date is 2025, May 30th. The time is 5:46 p.m. So that's 17:46. I know that this is probably the first time that I am recording this during the day, or during, while the sun is up. So it's still day now. It's not night. But for a reason. I hope it's a good one. I hope you find it's a good one. And the reason being that I have a lot of folders to cover. So apparently I have 34 folders to cover. So that's 13 plus 15, that's 28, plus 6, that's 34. Well, turns out I can do addition, adding, simple maths. So, well, at least I know how to do simple maths, adding stuff. So with that brief background out of the way as to why I'm doing this right now at this time, let's get right into it, because there is a lot to cover. I hope I don't go over 90 minutes. Maybe if I speed things up, I can do it in 45 minutes or whatever. But anyway, let's do this. So, in my very last video, I demonstrated that this is possible, given the setting where the learn rate method is proportionate tail and the candidate method is exponential tail, with the candidate percentage being 0.2, which I personally deem it to be the standard, because it kind of gives a robust entity distribution of the final state of the world, in the final state of the world. And well, so I demonstrated that given this setting, however the number of items change, it is very likely that some entities will hit the true ceiling. Even when the number of items fluctuate, they can decrease, they can then increase. And then I have also demonstrated that this is also possible, and this is a case where the era changes as soon as a condition is met, and that condition being the number of times an entity or two have hit the true ceiling. So for example, if it was 10 times, or if the true ceiling max count was 10, if an entity or if some entities have hit the true ceiling 10 times, or as in once per generation, but not in a row, those true ceiling hits don't have to be consecutive. But anyway, if the true ceiling max count is met, the era will change to the next one, where the number of items increase and the maximum constraint is is also set to increase according to the preset values. But because now there are more items, more genes that the entities can take. So after I've demonstrated this, I left off saying that I was curious as to if I could achieve the same when there are more than 5 eras, because as we've seen, and this goes on and on and on, this goes on and on and on and on, and as we've seen, hold on, this is some utility values, some util, and this is generation. So as we've seen, compared to what we have done before dynamic genetic algorithms, we've seen that if we use a setting where the distribution looked like something like this, and where this blue line is the true ceiling, and the x-axis is the sum utility in this case, and the y-axis is the count, entity count. If we feed in something like this, hold on, I think I have a better one. There, this is better. Let me just get something like this, and then can I get something like that. Hold on. If this is the true ceiling line, and if we were to feed in or use a setting where the entity distribution would look like this, and because the rest of and the rest of the entities were cut off, because going over the true ceiling would naturally mean that you are over the maximum constraint. So this is what would happen if things happened in one go. This is summed. This is the y. In this case, the x-axis is a summed util. I need this to be smaller, and then this is the entity count, because this is the distribution, the entity distribution plot, and this is 0 somewhere here. And if we did everything in one go, because the entities had all those generations to converge, the resulting distribution would look something like this. This is not pretty. Let me draw another one. Nope, I don't like that. See, that was Okay, whatever. Actually, fine, I'll just keep using this. Nope. Okay, so the entities would have all those generations to converge. For example, if 500 generations was given, if generations was set to 500, the hyperparameter generations was set to 500, the entities would have all that 500 generations for them to converge, and that would cause them to this is better. No, that would cause the entities. I'm really bad at this. I want us. Fine, this will do. No. I'm wasting so much time. This is better, I think, or not. Yeah, this is better. So that would cause them to that would cause the entity distribution, or the shape of the entity distribution, to shift to the right, because after converging to the true ceiling, all that's left for them to do is either go down in some utility value, or be struck out because you go over the maximum threshold. So that's what happens. But then if more than one era is set, or if the number of eras is bigger than 1, as the entities start from an era and proceed onto the next era, the distribution tends to shift to the left after every era, or in each era, or in the next era. So, but of course, they would still get higher summed utility scores in general on average, and they will still be converging to the next true ceiling, whether or not there was an increase or decrease in the number of items, or the increase and decrease in the maximum constraint value. But regardless, more eras mean that the distribution of entities start shifting to the left, like this. So if this was just one era, the whole thing, and then if there were 2 eras, it would go left a bit. If there were 3 eras, another one. If there were 4 eras, another one, another one, another one, another one, something like that. So that's what happens. And the reason I talk about this is that I wanted to see if I could, like I said, I wanted to see if I could get the same results given the default setting, and that is where the learn rate method is proportionate tail, and the candidate method is exponential tail, and the candidate percentage is 0.2, and preferably the number of generations is maybe 500, but because now there are because in the experiment that I'm going to talk about right now, because there are 100 items, increase the number of generations to 1000, and the pop size being 1000 as well, and maybe 2000, and then 3000 if things don't work. That's what I did, and all this to see if I could quite reliably keep hitting what could be considered the true ceiling. Now, I have to be honest, if there are 100 genes, 100 items, I would it could be very demanding, or it could be very hard. It could be very demanding, difficult to know the true ceiling, but which is why I had to repeat the same thing with different hyperparameters every time, or repeat the same thing with the same hyperparameters viewed a few more times. So I have a general idea. We can see that. But yeah, the whole point was to see see if I could keep on a consistently and constantly get a robust entity distribution while hitting the true ceiling, or very close to the true ceiling, with 100 items in total. So that's 10 eras. So that's what I did. Let's see how it went. So the first thing, the first setting is where the number of items would change, would start from 10 items and then go to 20 and then go to 30 all the way to 100 items per 100 generations. So yeah, oh yeah, I forgot to mention, the way I made up 50 additional items and utility values and constraint values is quite simple. I randomly sampled 50 values. I randomly sampled 50 values from the pre-existing 50 values, and allowing for repetition or replacements. So with replacement, and this is how it looks like. So this is the values list, or the utility values list. This is the constraints list, 100 of them. And of course, after 50 items, I didn't know how to name them, so from item 41, or the 41st item, all the way to the 100th item, they're all numbered, and they're all named and numbered so in this way: item 41, item 42, all the way to item 100. So very creative, I know. And this is the distribution of this is the distribution of utility values at every 10 items. So this is until 10 items, this is until 20 items, 30 items, 40 items, 50 items, 60 items, 70 items, 80 items, 90 items, and 100 items. So in this case, they're all kind of right skewed, not that much, but sort of right skewed. And this here are the distributions for the same thing, but for constraint values. And here, even here, I must confess that everything, even the first 50 items, were arbitrary. They were they're not actually random, but I made them up according to my own preference and to how useful I found them. But the sampling part was done with Python, so with replacement. So the latter 50 items and values, their respective values, are kind of random, and yet they're all kind of right skewed. But so far, I think I have demonstrated that distribution of values of items do not matter that much, at least not yet, at least not that I know of. They may matter in the future, but not as of now. So yep, coming back, the number of items will change from 10, 20, 30, 40, all the way to 100 at every 100 generations. So there are 10 eras, and the constraint values are also where are the constraint values? Constraint values are also set here. There we go. Now I have for today I have 2 sets of constraint values. This is the first set of constraint values for 10 eras. So until 9,000 here, it's what we have seen so far. The next 5 are the new constraint values, and the second set of constraint values is down here, but you can see that the max constraint values are somewhat lower. So I did this to the purpose of having 2 sets of max constraint values or max constraint lists were to set the environment so that the max constraint percentage when compared to the total constraint is higher for the first list and lower for the second list. And the reason for this is that in my past videos I have found that interesting things happen or start to happen around the maximum constraint percentage of 65 or 70, or otherwise just 60 to 75%. So the second list does that. This is where the constraint values, max constraint percentage per era is close to well 70, and once it goes all the way up to 82, but then it falls down to 76, 74, and the last 3 eras it's 69.7549%. The 9th era, that's the second last one, it is the max constraint percentage is 65.5124%, and for the last era it is the maximum constraint percentage is 73.3496%. So I have 2 sets of max constraint lists or max constraint values. So finally, again, back to the first setting, where the number of items start from 10 to all the way to 100, increasing by 10 items. And the actually no, again yes, sorry, take a deep breath. I'm in a hurry, I apologize, but I'm stuttering and making all these mistakes because I'm in a hurry, because there are 34 folders I would like to cover, and already 24 minutes have passed and I still haven't started with the first one. So the very first one, 1000 generations, 10 eras, 100 generations each. Number of items goes from 10 to 100, increasing by 10 items per era. The population is set to 1000. The learn rate method is proportionate tail or proport tail, and the candidate method is export tail or exponential tail, and the candidate percentage is 0.2. And every entity here has the individual mutation rates according to their rank in the world in that generation. And here we go. So here's that 100 generations to 120 for no reason, but at 200 generations we have hit the true ceiling, that is 710, and 365 for the first 100 generations, or after the first 100 generations. After 300 generations we have hit the true ceiling again, what is supposed to be, what is likely to be the true ceiling. Even for the fourth era, 1135, fifth era, 1540, that is very likely to be the true ceiling. And the fifth era, it's 1760, we don't know if that's the true ceiling. And seventh era, it's well, 1900, we don't know. And at after 1000 generations have passed, the maximum ever is 2930. So let's just write that down somewhere. So and this is when I used the higher max constraint list. And there we go. What was it? 2930. 2930. Yep. So that goes away. 33 more to go. And in the next one, I increased the size of the population from 1000 to 2000, with everything being the same. And here we go. So there, we've seen this. After this. For now, I'm only going to focus. I'm mainly, not only, but mainly going to focus on what the true ceiling may be when num items or number of items is set to 100. So in this case, when the population was doubled to 2000, the maximum ever is 2935. 2935. And in the next one, it's the same thing. And what changed? In the very next one, the only thing that changed here was the number of generations. I don't want this. There we go. And the population is still set to 2000. So 365, 710, 945, 1135, 1540, and then the last era, it scores the maximum ever is 2970. So we're getting higher values. I mean, that's progress, I think. And in the next one, what did I do in the next one? It is still 1,200 generations, and now the population is at 3,000, with the learn rate method and the candidate method and the candidate percentage still being the same. That is respectively proportionate tail, XP tail, and 0.2 or 20%. And for that, we get this, and now the maximum ever has reached 2980. That's good. And in the next one, what did I do? Well, the next one, the population is at 3000, and now what changed? Yep, 1000 eras. I'm just looking at my notes or my code. That one, yeah. Oh yeah. So in this very next one, I wanted to let the entities have the entirety of 1000 generations. So there's only one era, right? And this is what you get. And in this case, the maximum ever is 3030. So let's just write that in. Is this the best one? We don't know. Spoiler, it's not. But yeah. So right now, what I've done is that if I feel that it could be better, or if I feel that I want to try harder, I would just throw more generations or throw more entities at the problem, which I know isn't always the wise thing to do. Just a second. Okay, I'm back, and in this one, the sixth one, still using the higher maximum constraint list. What did I do? The population is set to 3000, and I have 10 eras back again, and each era is 100 generations long, so it's 1000 generations, and this is supposed to be the same as well, not really the same, but we'll see. Oops. Yep. Now, in this case, well, now it's down to 2995. So write that in, 2995. A good way to scan if this could be if this maximum ever could be the true ceiling, I think, is have a look at the final population. If it's exactly the number you set it to, in this case 3000, I have found that in that case the maximum ever that you got is likely not the true ceiling, because what usually happens is that if the true ceiling has been met, and quite often at that too, it would mean that quite a bit of entities will be struck out, and therefore the final population, or in the population size in after or per generation, within that generation, or at the end of a generation, is smaller. So if you set it to 3,000, it could go down to 2,700. If you set it to 1,000, it may go down to 910, something like that. So in this case, it's 2995. So likely not the true ceiling. Next thing I did is now the population is up to 4,000. See, I'm now throwing more entities at the problem because I feel that I'm not getting the true ceiling or true ceilings. So now the population is at 4,000. Minus 6 here, and there we go. Now it's 3005, and you can see that it's one big era because there are no steps here. So it's 3005, 3005, still not as high as 3030. And in the next one, now here, what I've done is it's still one era, probably, but the population is back down to 1,000. However, with the learn rate method and the candidate method being the same, the candidate percentage has been increased from 0.2 to 0.5. So now the percentage of entities that get to learn is 50% of all entities of the world within that generation. And we'll see what happens. There we go. Now, because the candidate percentage has been increased from 0.2 to from 0.2 to 0.5. See, now it's 0.5. The maximum ever is 3055. So that's the highest we've seen so far, right? But this is still in one big era. Okay, so we're doing and not doing these steps or changing eras or dynamic genetic algorithm. We're ideally you would do this to find what can be. I'm doing this in order to find what can be the true ceiling, and once I do have a general idea of what the true ceiling is, or what could be considered as very close to the true ceiling, then I do the dynamic way. So the next one I did is this, and now here, with everything being the same, the candidate percentage is at 1%, or I mean 1.0, meaning 100%. So every entity in the world within that generation get to learn. Yeah, every entity gets to learn, and when that happens, the maximum ever is 3065. So 3065 is at best. We don't know yet. So just having a look. So that was with when the candidate percentage is set to 1.0. Next thing I did is This is still the same, except now we have the population set to 2,000 entities, and the generation still being 1,000, and we still get 3065, 3,065. So it's 65. Is 1, 2, 3, 1, 2, 3, 1, 2, yeah. So the next one. Now that we kind of think that 3065 is the true ceiling, we're doing the dynamic again with 1,000 generations, 10 eras, 100 generations per era, and with the candid percentage being 1.0, meaning 100%, and this is what we get. And the maximum ever in this case was 3060. So quite close. So I think that was okay. But the only problem there is that the resulting distribution looks like this. Of course, this, when you have the candid percentage at 1, the resulting entity distribution looks something like this. Everything that's on the left side of the red line. But since there are 10 eras, the distribution started shifting to the left, and in the end this is what we got. So something like this. A good way here to also look if something is working or something is likely to have entities that keep on hitting the true ceiling is to have a look at the mode, how high the mode is, the mode entities, and how many there are, of course, because if the mode is close to the true ceiling, it means that on the right tail entities would have hit the true ceiling. Or rather, if the value for the mode of in terms of summed utility value is close to the total utility, meaning the sum of utility values of all items, not considering the maximum constraint, or when the maximum constraint percentage is at 100%. So if it's very close to the red line, if the mode is close to the red line, you are likely to have more than a few entities that hit the true ceiling. But anyway, because I have the candid percentage at 1.0, well, it kind of worked, or it is kind of working, but I don't like the fact that this is just a personal opinion, but then again, I remember that having a robust entity distribution is desirable, because you never know how the conditions will change in the future, which is the actual very purpose of doing dynamic genetic algorithms. So because of that, I would like to keep to the normal shape, but in this case that wasn't the case. In this case I didn't use that, so that's the only qualm I have for this. Next one, I still used the I still have the candid percentage set to 1.0, 100%, but then I changed and the population is still set to 1,000, but I changed the number of generations it was given, and this is what I got. Now we have 3065 again, so we go back and then 3065, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. Is that 12? Yeah. And then now this one, we have the maximum ever at 30, 45, and this is when the candidate percentage was lowered to 0.5 or 50%. So now it's 30, 45. So it is very likely that 3065 is the true ceiling when it comes to 100 items with a higher, with higher max constraint values. Where's the color for the? Oh, there we go. No, please don't. So, and then, but like I said, interesting things happen. Oops, interesting things happen when you have the when you either set the maximum constraint percentage at around in the range of 65 to 75%, or when you have resulting maximum constraint percentages in that range. So I lowered it, and so the second, when I have lower maximum constraint values, and that's what I'm going to demonstrate now. So the first time, the first thing I did in this case, I wanted to find what could be. I wanted to use the setting where everything is done in one era for 1200 generations, with the population being 2000 and with the candidate percentage being 1.0 or 100%, learn rate method proper tail, and candidate method XP tail, and individual mutation rates. And this is what happened. Is this? No, that's until. This is what happened. The maximum ever in this case was 2840, but we don't know because now this is again uncharted territory. So we go back and then we write 2840, and in the next one I did is now we have 10 eras, proper tail, XP tail, candidate percentage 0.2, population 1000, and 10 eras again, like I said, but 100 generations per era. And this is what we get. And the maximum ever here in this case is 2740. So 2740, and we leave a question mark to keep on wondering if 2840 is the true ceiling. Spoiler, it's not. And in the very next one, I'm going to increase the candidate percentage to 0.5, so 50%. And in this case, the maximum ever reached 2820. So that's a bit higher. So we're getting some progress again, but it's still lower than 2840. So in the very next one, Now the candidate percentage is increased to 1.0, and here the maximum ever is 28.05. So somehow we got very unlucky. Now we have lower maximum ever value despite the higher candidate percentage value. And the very next one, in this very next one, 1200 generations and still a population of 1000. Yes. So this is just like that last time when it gave us 2740, but with 200 additional generations, and this is what we got, 2785. So let's just write that. It is still higher than 2740, but this is the result of 200 more generations, so I don't think that's a lot of improvement. Still an improvement nonetheless, but yeah. And in the next one, now we have the population increased to 2000, and the number of generations is back to being 1000. That is 10 eras and 100 generations in each era. And now, yeah, so let's have a look. There we go. And now the maximum ever in this case is 2780. Let's just write that down. So not an improvement. And in the very next one, it's the same thing, but with a higher candidate percentage value. And now the maximum ever is 2820, but still not as high as 2840. So we move on. Oops. And in this one, what is different? Oh yeah, everything is the same, except that now in this case the candidate percentage value has been increased to 1.0. So that's 100% of the entities will be learn candidates, and in this case maximum ever hit 2815. So 2815. So still not really hitting anywhere close to 2840. And in the next one, yeah, and in this next one, everything is back to default, but as in the candidate percentage is back to 0.2, and the population is back to 1000, and the number of generations is 1000, but we only get one era. And in this case, the maximum ever was 2810. So that's 2810. And the next one is still the same, but the now we have double the population. So now it's 2825 when the population is close to 2000. See, and now the final population is 1949. So we had 51 entities struck out. Well, struck out and limited, but then again, yeah, I think I covered that. So there's 28, 15, is it? 25. Yeah. And in the next one, this next one, oops. Now we have again 1 era, 1,000 generations, and 1,000 entities in the population, and the candidate percentage has been well, raised to 0.5, as in 50%, and now the maximum ever in this case is 2830. So still getting there, but not 2840 yet. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And in the next one, 1 era, like we've done, and just the candidate percentage back to being 1.0. So very much like the first one we did, where it was where the generations were set to 1200, but in this case it's generations is set to 1000. And now we have 2840 again, when given a very extreme distribution, when using a very extreme entity distribution. So it seems that all hope is lost, doesn't it? Well, yeah. And in the next one, what did I do? So in this very next one, going more extreme, instead of having the candidate percentage set to 1.0 and giving it 1000 generations to converge, now I gave it 2000 generations to converge. See what happens. Now the maximum ever is at 2845. 2845. Just some water. So we got 2845, and in this one we got 2790, and this was from the setting where I had 2000 generations, 2000 entities in the population, and the candidate percentage back to 0.2, as in 20%, and we have 2790. So again, when candidate percentage is lower, for example 0.2 or 20%, the maximum ever doesn't seem to go over 2800. That's sad, but wait for it. And in this next one, yeah, I did this one for fun. Oops. This one I did for fun. This is when, although it says 0.2 here for the candidate percentage, what happened here is that within every generation, the candidate percentage was chosen to be either 0.2 or 1.0, so it was random. And even when I did that, we have the maximum ever at 2790. Amazing. 3, 4, 5, 6, 7, 8, 9, 10, 11. What? 13, 14, 15, 16. No, wait, what? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Is that right? Yep, that's right. So, 15 of them. So, now I'm in despair because I wanted to use a more normal looking entity distribution shape per era, and none of that actually went anywhere close to the true ceiling. It's not like I don't want any entities to be near the true ceiling or hit the true ceiling. I don't want all of them to converge on that. I just want some of them to converge on that, so that when things change, the robustness of the population is preserved, or rather the entities are preserved because the robustness is so high. But, or so, I tried something else. In this one, what happened is that while using the lower maximum constraint list for this one, while using the lower maximum constraint list, the generations was set to 1000, so and 10 eras, and 100 generations each, and the population was set back to 1000, and the candidate percentage was set to 0.2. No. Why did you do that? Can I restart? Yes, please. And when I did this, no, actually, the only difference here was I lowered the base mutation rate because I was just reading some things on the internet as I googled for stuff, and then I found that the mutation rate is far lower per gene, lower than 0.03 or 3%. So in this case, I lowered the base mutation rate to 0.015, as in 1.5%, and you can see that here. It used to be 0.03, as it shows here. I first lowered it to 0.015. So now I'll just briefly draw that. I'll briefly demonstrate that. This is the world, and this is the plot for mutation rate, and this is the head entity is here, the tail entity is here, and give me something like this, something like that, and here's the median. So before, when the base mutation rate was 0.03 or 3%, this would be 3%. and the tail entity would enjoy or suffer the mutation rate of 6%, and the head entity would have an individual mutation rate of 0 or something very close to 0 in a linear fashion. But now with the base mutation rate gone down to 1.5%, this becomes 3% for the tail entity. Yeah, and for the head entity it's still close to 0. So when I do that, this is what I get. I have a maximum ever at 2860, and I was using a 0.2 as the candidate percentage value. So suddenly we have a very high, a higher value than 2040. This is lower mutation rate, MUT rate. It's well, I know MUT is not a nice word, but anyway, I'll find mutation rate. Lower base mutation rate, fine. Yeah, that's amazing, isn't it? So I wanted to check if this would be the same for the higher max constraint. So that's what I did. Same thing, except now I use the higher maximum constraint list, and this is what I got. 0.2 for the candidate percentage, and the maximum ever is 3060. I know it's not 3065, but when I did that, I rarely ever got a maximum ever value higher than 3000, but now it's above 3000. So somehow the lower mutation rate seems to preserve entities with higher sum utility values, of course, or not, because if you think about it, the head entities already enjoy a mutation rate of something close to 0. But now in this case, it's a question of preserving these guys, the top entities, the high entities. Why is it so hard? These guys here. These guys, because now they would mutate at a lower rate per gene. So 3060, even when using 0.2 for candidate percentage. And next thing I did, so the good news is that I still get to use the setting that gave me the robust entity distribution, and I'm still using 1000 entities for the population. It's still 1000 generations, so it's the standard default setting. Yeah, so this next one did the same thing, and now it gave us 3060 again. That's quite consistent, so it's good news. This was good news. And then the next thing I did was I lowered the base mutation rate even lower. I made it even lower, so it went from 0.015 for yeah, and then for a while, and then now it's back to, it's lower all the way down to 0. What was it? Oh yeah, 0.01. So 1%. So with that, now this becomes 2%, and this in the middle, it's 1%, and this is still close to 0. Okay, so when I do that, this is what I get. Still using the default setting, what I like, the standard setting, and now I have a value of 3065 for the maximum ever. So that's good. Not using, even when not using an extreme entity distribution shape, I think I think that's very good for the robustness. And the next thing I did, what else did I do? Yeah, and the next two other tries that I did was the same thing, just to see how reliable this is. See, 3050, so lower than 3060 or 3065, but you know, still quite satisfactory. And the last one, 3065. And what's even more surprising is the number of entities in the final population being 1000. So what I said about this being a quick way to judge is not that applicable here. You can't really say that works here, but still. And the peak is quite close to to what could be considered the true ceiling. And this is the distribution. See, what's well, it is quite skewed, and a lot of entities are at 3060. But I think yeah. So a lower base mutation rate could be said that a lower base mutation rate skews the distribution to the right, or shifts the distribution to the right, like that. What used to be here could now be moved here. So far, I don't know if that's necessarily a good thing. It could be, I mean, using a lower base mutation rate could be another way of me applying applying some extreme shapes in terms of the entity distribution. But so far, it is quite intriguing to see that this happens. Yeah. So that's about it for today. Wow, 1 hour and 15 minutes. but it's very interesting, and I'm still wondering whether I should stick to this setting, or where I lower the base mutation rate and use the individual mutation rates, etc., etc. Tell me, what happens if I use the entire thing, one era, then 0.2 for 1000 generations? That is this one, lower dash 8. Yeah. So this is what the distribution looks like with the standard setting, default setting, candidate percentage being 0.2, learn rate method being proper tail, candidate method being xv tail, 1000 entities in the population for 1000 generations, and the number of items being 100, and for the lower constraint list, lower max constraint lower max constraint values, to be exact. But I don't think what I did so far changes the fact that you still need to be feeding in somewhat very converged shapes into these eras. Be using these converged shapes, very converged shapes, like something like this, like half a curve, something that looks like half a curve, in order to proceed onto the next era and produce entities that hit the true ceiling every now and then. Yeah. But I find it a small win that I don't have to increase the candidate percentage to 1.0 from 0.2, because I don't want to have all the entities learn, because that's just a lot more to compute. For example, if it was set to 1.0, 100% per generation, then that means 1,000, close to 1,000 entities will have to go through the learn function, learn from other function, which is a lot of work. So a way to avoid that would be to have a lower base mutation rate and use individual mutation rate. So I'm still somewhat happy. Yep. Okay, that's about it. Thanks for watching, listening. Goodbye.